Hello again, welcome to the Academy. This is part of a video series on Calc 3 topics, and this time we'll be talking about double integrals. So previously, I talked a little bit about line integrals, path integrals, which were single integral generalizations of an integral for multivariable functions and for vector fields. And I want to talk about another type of integral, the double integral. So the basic motivation behind this one is if we have a function like this, and instead of finding the area under a curve, is you find the volume under a region. So you have a region like this, region R, and you say, well, if I take this region here on the function, what is the volume underneath this region? Basically, this green volume, which is the volume under the curve, under this curved surface. And there are ways to calculate that, but basically, let me just start off by sort of attempt to have a definition, kind of. So basically, the way that's done is you take your region R, which is going to be some region in the xy plane. What you want to do is you want to divide it up. At least this is the formal way of doing it, into small sections, and they can be any shape and any size, really. And there's going to be a point in every single one of these. And say there are n regions and subregions, I guess. And what you would do is you would take each of these points, you get number it from 1 to n, and then you would find, to give an approximation, you would add up the function, this is your function f of xy, you would add up the value of the function at that point, xi, yi, times the area of the base to get the area of the prism. So delta A, for each one of these delta A, I. So each one could be the same area, but it could be different area depending on how you slice this region. I equals 1 to n. And that will give you an approximation of the volume, and then we say, well, as n goes to infinity and we get smaller and smaller subregions, this will approximate the true area, which is the double integral. We have two integral signs to show that's a double integral. Technically, you don't need two integral signs, but it makes it much more clear. So you're integrating over the region R of f of x, comma y dA. So delta A becomes a dA, representing, of course, I guess intuitively could be an infinitely small piece of the area. So how can we actually calculate this integral? Well, let's start with an example. Let's consider a function that we've seen many times, x squared plus y squared. I know what this looks like. Looks something like this. Let's say we just want to do a simple region, just the unit square. This is 1 by 1 square. in the xy plane. So the region will probably go something like this. So that will be the volume in that area. So we'll consider it at this point. And so let's think about how can we try to calculate this. And so one way of doing it is if we think about this as slices, we try to find slices of this region. So say we have a x value, pick a random x value x, and if we hold x constant, we get a slice of this region. And we can find the area of this by a single basic integration. So basically, you just take this x value, whatever it is, and you say this is a fixed x value, and you just consider this slice of your function f of xy with x fixed, and we call it x1, I guess, just to differentiate it. So x1, and what you can do to find this area is, of course, just integrate it from how does y change? Once y goes from 0 to 1, y. So this is a function of y because we fixed x1 as a constant. But now if we vary, so this whole thing is the area of this slice, red slice, at x1. Or if we want more generally at any x value, at any arbitrary x, we just say at a value of x, this is the area of this slice. So this depends on what value of x we choose. I'll give you an area. But now if we think about every single x value here having y slice area, we can say, well, if we take all of the slices of this and we add them all up, we'll get the whole region. So we can actually take this new function of x and we integrate it again, this time with respect to x. So we're taking this slice value, so this is the area of this slice, and we're integrating the area of x dx. So this area depends on x, like we said. And so if we integrate the area, we get the whole volume. And x in this case goes from 0 to 1 again, which is integral from 0 to 1, and the integral from 0 to 1, f of x on y dy dx. And a lot of times you'll see that the parentheses are dropped. So you see that we've turned this double integral over this region R, this square, of f of x comma y dA, turned it into an integral, or a repeated integral of an integral. It's an integral within another integral. And in fact, there's a theorem for special regions like these. In fact, there's two types of regions. There's something called vertically simple and horizontally simple. Vertically simple just means you have a function like this. Where all of the vertical lines, you can slice it vertically without the lines ever leaving the region. So this is a vertically simple region. And horizontally simple, just the other way around. Where you can have horizontal slices, but maybe not vertical slices. So basically this one is just a region that's between two functions, the g of x and h of x. And this one is the other way around, just functions of y, g of y and h of y. Actually, let's call this one g of y, h of y. You can see here are two different functions. Let me just draw them in different colors. This is g of x, g of y. And here's h of x. And here, h of y. So, this is horizontally simple. The theorem basically says well, the two cases for vertically simple and for horizontally simple. Vertically simple says the double integral over this region R of xy dA is equal to the integral. Let's say this x value goes from, I don't know, a to b, and this y value goes from a to b. That's these points right here. That's these points right here. And that's integral from a to b of the integral from g of x to h of x of f of xy dy dx and for horizontally simple, you just reverse the order. You're going to slice in this direction, the x direction first. So you're going to have dx on the inside. So the double integral dA is equal to or equivalent to an integral of an integral, iterated integral 1 g of y to h of y of f of xy dx first, then dy. And so one thing to notice is that when you're taking integrals like these, multiple integrals, they have integrals on the inside of other integrals. The outside will always be numbers, a and b, in this case. And you'll never have a function, like in this case, you have functions inside, but you can't have outside. They have outside, then you know you did something wrong. Because it has to be numbers, because when you substitute it in the end, you don't want variables, because it's going to be a volume in this case. A volume can't be having variables in it, it's just going to be a number. And so one thing to see here is, again, horizontally simple is going to be dx dy, and vertically simple is dy dx. And you can understand that dx dy and dy dx, again, this comes from the idea that if you slice the area, let's say you slice it in little rectangular parts, delta x and delta y, you multiply delta x times delta y, the area of the rectangle will be delta A. And of course, in the limiting case, when we're talking about the limit that makes dA equals dx, dy, or dy, dx, same thing. Of course, there are different cases in which you would want to use them. So just to do another example with more complicated functions. Let's say we have a function. Actually, no, let's actually first just calculate this one, just to get used to it. So f of x, y was x squared plus y squared, and that was just the, what was this, 0 to 1, 0 to 1, y dx. So first what we want to do, of course, is evaluate the inside integral. So in this case we're treating x as a constant because we're only integrating the y. So it's going to be integral 0 to 1 of, well, the integral of x squared, well, that's the constant, it will just be x squared y. So that's going to be y cubed over 3. And then this is as y goes from 0 to 1. So this would be, what is this, x squared. And then we'll put 0 in for y is 0. And this is 1/3 minus 0 again. So now integrating this, we get 0 to 1, integral of x squared, x cubed over 3. Plus 1/3 x from 0 to 1, so that's 1/3 plus 1/3, which is 2/3. So that's that integral. And let's see another integral that's slightly more complicated. This is the same function, but this time what if our region well, let's just say it's the unit circle. So this is R, the circle with radius 1. Well, to integrate this, you're going to break it up into functions. So is this a vertically simple or horizontally simple? Well, actually, it could be both in this case. But the equation of this is x squared plus y squared equals 1. We can solve for y. Y is plus or minus square root of 1 minus x squared. So basically, you have two functions here, one on the top and one on the bottom. And which is, this will be positive square root of 1 minus x squared. This will be the negative square root of 1 minus x squared. This goes from negative 1 to 1. So we can set up the double integral. So the double integral over the region R of x squared plus y squared dA is, well, we said it's negative 1 to 1. And then y goes from, for any given x, it goes from negative square root of 1 minus x squared to the positive square root of 1 minus x squared. dy dx. So again, integrating the first part is not that bad. We just get, again, x squared y plus y cubed over 3 going from negative square root minus x squared, positive square root of 1 minus x squared. And so, well, we just substitute it. Negative 1 to 1. So it becomes x squared square root of 1 minus x squared plus, well, if we cube this, we just get 1 minus x squared times square root of 1 minus x squared over 3. So minus, what have we put in the negative? So minus negative, so x squared times negative would be negative x squared square root of 1 minus x squared. Plus, well, if we have the negative cubed, it would be a minus. That would just be the same thing again. Dx. This is a very complicated expression. We can simplify it a little bit. Go over here. It's equal integral from negative 1 to 1. Let's see, so this minus a negative of this, so 2 of these. Plus, well, we're going to do 2 of these as well, because minus the negative, so it'll be 2/3 minus x squared times square root of 1 minus x squared. And we can sort of simplify this a little bit more, maybe factor out the 1 minus x squared, or the square root of 1 minus x squared. Minus 2/3 x squared is how many x squared? So that should be about 4/3. Right. So this is not a very simple integral to compute. It can be done in this form, but I'm not going to do it right now because, well, the way you could do it, you would distribute this again, split it up into 2 separate integrals. This one you could do, actually you could probably do that part pretty easily, kind of by inspection or by some kind of trigonometric substitution. And the same thing with this part over here. You can do some substitution that will probably do it. But there's a simpler way to find the same integral, and we'll see more about that next time. So right now, let's leave you with this thought right here. If you want, you can try to do this integral on your own, but you'll see it's not very nice, or it's not very easy to do. And next time we'll talk about some methods that will allow us to solve integrals like these. And that's all for this first part of double integrals. Thanks for watching, and I'll see you in the next video.